In the early days of a solar system's birth, planets do not always stay neatly where they formed. Instead, they can wander, sometimes drifting inward toward their star, other times moving farther away into the cold reaches of space. This process is called planetary migration, and it has radically reshaped our understanding of how planets, including those in our own solar system, found their present homes. Planetary migration begins in the swirling protoplanetary disk of gas and dust surrounding a young star. As newborn planets form, they interact gravitationally with the disk, creating ripples and spiral patterns. These ripples exert a push or pull on the planet, gradually altering its orbit. Sometimes the effect is subtle, shifting the orbit over millions of years. In other cases, it is dramatic, dragging a giant planet close to its star in a relatively short cosmic timescale. One of the most striking pieces of evidence for planetary migration comes from the discovery of hot Jupiters, gas giants similar in size to Jupiter, but orbiting scorchingly close to their stars, often in just a few days. This was puzzling because such massive planets are believed to form far from the heat of their star, where ices can condense to build their enormous cores. The only way to explain their current positions is that they formed in the cold outskirts, then migrated inward through gravitational interactions with the protoplanetary disk or with other planets. Migration is not limited to giant planets. Smaller worlds can also shift orbits, sometimes leading to resonant configurations where multiple planets lock into rhythmic patterns. This can stabilize their movements, or in more chaotic systems, destabilize them, causing collisions or ejections. The early solar system may have experienced such upheaval. The NICE model, a leading theory, proposes that the giant planets Jupiter, Saturn, Uranus, and Neptune migrated significantly after formation. In doing so, they scattered countless asteroids and comets, triggering the Late Heavy Bombardment, a period of intense impacts that scarred the Moon and other worlds. Planetary migration has profound consequences for habitability. If a planet that could once sustain life is pulled closer to its star, it may overheat, losing its oceans and atmosphere. Conversely, a frozen world might move into a star's habitable zone where liquid water can exist. Such shifts can therefore create or destroy opportunities for life to emerge. Our understanding of migration comes from both observations and computer simulations. Powerful telescopes reveal planetary systems in various stages of formation, while advanced models allow scientists to test different migration scenarios. By adjusting factors like disk density, planet mass, and gravitational resonances, researchers can reproduce many of the strange arrangements we see in exoplanet systems today. Far from being static, planetary systems are dynamic, restless creations. The planets we see now, whether scorching hot Jupiters or icy wanderers, are often the survivors of a turbulent cosmic dance, their current orbits the result of millions of years of gravitational give and take. Planetary migration reminds us that in the grand architecture of the cosmos, change is the only constant.